All right, so it's 10 a.m., guys. Let us begin. All right. So if you have cameras, I prefer them on. You guys know the deal. It's only been a week. I'm sorry that we have to do this. Wish you guys could have the day off. Unfortunately, that's not the case. So let's see what we got. I released the quizzes this morning, so you should be able to see what you've got wrong. Everyone else who took the pumps quiz, your grade will go up shortly. Haven't graded it yet because haven't been on campus. Now, everybody has taken both pumps, valves, and piping. So like I said, all three of those are open. Usually we would be reviewing these the day, the next class. But for the most part, we had a couple late comers to the class, so we had to take care of and make sure they would be able to take the quizzes fairly. So if you want to open up and see what you got wrong, we're going to go over it real quick. We're going to do all three of the quizzes pretty much in succession. All right, so what I have open is basically the statistics of what you can see of what's gotten wrong, everything along those lines. All right. So for question number 1, which of the valves listed below will cycle from fully open to fully closed when the handle is turned 90 degrees? All right. Pretty much all of you got it right with the butterfly valve. All right. No one got a check valve, which is good, and a globe stop valve. I don't even think that is a valve. All right. So got to watch out for those. I just make up words sometimes, all right, before you guys will actually be able to do these things, all right? So watch out for those. Gate valves cannot be used to throttle due to what? Again, pretty much everybody got this right. Eventual wear of the disc causing leak by for the 5%, all right? You can accurately show how open the valve is, all right? So when you open up one of these valves, you're basically going to be opening it up, and when the stem stops extending, that's when the valve is fully open. And when you turn the handle all the way down and it stops going any further, that's when it's fully closed. All right. So the difference between a relief valve and a safety valve is a relief valve will open and reset at the same pressure, whereas a safety valve will open at a set pressure but reset at a pressure below that. All right. Regulating valves can be controlled by what means, all right? And it can be controlled by everything. Remember that one slide that was like, if we can measure it, then it can happen. So you got temperature, flow, level, pressure, literally anything that is measurable, we can take it and put it into a regulating valve, all right? Next up, we have a valve below. What valve below can be used to throttle without other valves in that line, all right? If you remember correctly, the butterfly valve on this list is the only throttle valve, but there was another valve that if we had 2 valves in line, what would be that other valve?
The gate valve.
Gate valve, correct. All right, in the picture shown below, the pressure being regulated is the closing force. All right, so we have flow going through. Everyone can see my mouse, right? All right, cool. Comes up from below and it's going to go down this direction. All right. And as we look up, we have this little line right here. It comes through and it's going to be going on to the bottom portion. All right. So that's going to be pushing upwards, countering the spring force and closing the valve. All right. In the picture shown below, the valve is maintaining what type of pressure? It's again the same valve. We see flows coming from below and over. All right. Coming from below and over there. All right. So it's coming and it's maintaining the downstream. Remember, it's in relationship to where you are referencing to. All right. We're referencing this valve in line. So upstream is going to be over where my mouse is circling, and downstream is going to be in this direction. All right. True or false, a bypass valve is used to direct flow and isolate a piece of equipment to allow to continue operation. All right, that answer is true. It's a bypass. You are bypassing a certain type of equipment, a piece of equipment. Finally, true or false, a swing check valve allows flow in either direction when mounted vertically. All right, that answer is false. All right, we have a swing check valve. It's going to be basically swinging and going either way. All right, it can be going vertically or it can be done horizontally. What check valve wouldn't work if it was mounted vertically?
Lift check valve?
A lift check. All right, so that would allow flow in both directions if it was mounted vertically. All right, because it wouldn't be working as intended. And then this is the one where you all kind of struggled here. You can see a lot of people had a split difference there. The packing gland main purpose is to provide an area where packing material can be inserted to create a watertight seal around the stem. All right, so if we pull up this. All right, so we have our valve. All right, so that we're going to say is the packing gland right there. It comes down into the bonnet. All right, and then the body would be down here. All right, so this is the area where that gate is going to be. So there's the gate valve itself right there. We'll draw the stem in green. Come on. All right, there's my stem with all of the threads on it. And then we have this area for packing material. All right, so it's almost like a thread-like material that you would put in via rings. All right, and you would pack it in around. So it's going to be, it will come in a long strand, almost like basically a roll of rope. All right, but you can't just stick rope into it. So you're going to cut it at a certain length, and then you're going to roll it around. All right, and it's going to come and look like that with the stem going through the middle. All right, so there's the stem right there. All right, and then you have the actual packing gland going around it like that. All right, so that is what we're trying to do here. So we're going to have a packing material that's going to go around it, and you're going to have about 3 to 4 layers here. All right, and you're going to have it alternating. So if on one time you have the break over here, the next time you're going to flip it 90 degrees and the next layer is going to have a break over here. All right, and the next one's going to flip and go again onto the other side. All right, and that's your packing gland right there. And what you would have on top of it is actually a piece of metal with threads through it. It's going to go around the stem as well, where it's going to be pushing downwards and squishing that packing material. All right. Let's see if I could pull up physical picture. All right. So here we go. We have different spots here. All right. Let's see. That's super small, of course. Wouldn't have it any other way. All right, so that's the rope-like material that you could be having here. All right, and as you go through, you can see here is the area that's going to be tightened down and pushed into it, and then those spots with the X's are the actual packing material. All right, again, you can actually see it. There's a line of packing material right there. You can actually see it's quite large. There's some other ones right here. All right, so there is that. Any questions on the valve quiz before we go on to the next one? Nothing? All right. On to piping. All right. So when creating threads on a pipe, you need what type of tool? All right. The tool itself is going to be a tap and die. All right. Tap is for interior threads. Die is for external threads. All right. So that's going to be universal. A union will create a watertight seal due to what? That's the metal and metal contact, all right? All those photos that I posted into the PowerPoint area, all right, those were all creating a watertight seal due to the metal to metal contact, all right? The threads were just creating the force to allow that seal, all right? To make a 90-degree turn with piping, what type of fitting would you use? That would be an elbow, all right? For the 5% that use the T, that is, you could do that, but what else would you need to stop it from just pouring out the other side? What type of fitting would you have to add?
Would you have to add a plug?
Yep, you can add a plug. All right, the other thing you can do is you can add a section of piping and then put a cap on it as well. All right, so if you guys are in a bind, you can always get creative, all right? When you have to join two pieces of pipe together, while one end is connected to the bulkhead, while the other is attached to equipment. All right, so we have two pieces of pipe. Both are attached on either end and can't be unscrewed. All right, if we use the coupling and we thread it onto one side, the other side, as we said in class, is going to be de-threaded, right? It's going to get loose. So we need to utilize a union, all right? Piping with a diameter exceeding 14 inches is sized by the outside diameter. All right, this is just a actual memorization, all right? This is an is what it is kind of question. True or false, nipples can be used to combine two pipes that have internal threads. That one is wrong. Oh no, sorry, I'm thinking plugs. I'm sorry, only had one cup of tea this morning. So, almost scared 81% of you into thinking you got another question wrong. All right, so nipples can be used to combine two pipes that have internal threads, all right? And those could be the ones that we showed that were really tiny and microscopic in size, right? And then the ones that were quite longer. All right. So true or false, when bolting up flanges, you should bolt clockwise. That is false. All right, what's the pattern that we are looking to do? No matter how many bolts there are.
Star.
The star pattern. So choose one spot and then start starring it from there. All right. When schedule increases, what happens to the pipe? As your schedule increases, your wall thickness increases. All right. What happens when your schedule increases as well? The outside diameter is not going to increase, correct? That stays the same. Inside diameter does not increase. We have to increase our wall thickness. All right. When sweating a copper pipe to a fitting, flux is used as what? All right. Flux, remember, liquefies. It's going to boil off and create a vacuum inside of it once it boils off. And as that vacuum happens, the solder that you're going to be utilizing is going to heat up and flow into the joint and fill the entire joint with solder. All right. That is the entire purpose of flux. All right. So true or false, pipe thread is different from machine thread, and that is 100% true. You cannot use a pipe die and tap set on anything if you're going to be utilizing any sort of machine threads. All right. Any questions on that? All right. Let's go into pumps. So let me see what we got here, because I actually haven't looked at this one yet. A double acting reciprocating pump sends out how many volumes of liquid per cycle? All right. So remember, if it's a reciprocating pump on both sides of our piston, and one cycle is a full one up and down. All right. It is not just one straight up. All right. It's a full cycle. All right. So we have 2 volumes. All right. A Wilden pump is a what type of pump? The only pump that it is a positive displacement. All right. What is the technical name for a Wilden pump, even though it's an industry name?
Diaphragm pump.
The diaphragm pump. All right. So if it's not positive displacement on this question, it might be diaphragm. All right. To increase the pressure of a centrifugal pump, what can you do? All right. The only thing that you can do without changing anything too crazy would be to increase the speed of the pump. All right. Installing a smaller impeller would not increase the pressure. All right. Installing another pump in parallel, we didn't learn anything in that sense. Okay. So you got to watch out for those, just because it sounds like it would be correct. All right. Remember what we've learned in class. All right. And you cannot increase the pressure of a centrifugal pump without replacing it. That is entirely incorrect. All right. All pumps have a slight range of what they can be run at. Okay. Some of them will need to be replaced if you need to go crazy, but if you just increase the speed of the pump, you will be able to increase your pressure. All right. And you can decrease your pressure via decreasing the speed of your centrifugal pump as well. All right. Shut-off head at a centrifugal pump is what type of scenario? All right. Remember our charts that we utilize. All right. So if we have our chart, we have flow on the X, and we have pressure on the Y. All right. We have our ideal line, which seems to be going off on a nice little angle. All right. And then we have our fall off pressure for our pump. And what we're looking for is our no flow scenario. So we're going to be existing, I'm going to go nice and dark on that one. We're existing right there because we're having 0 flow. So we have nothing on the X axis. All right. So where we exist is going to be right at that singular point. All right. At a set pressure with no flow. All right, multiple choice. A relief valve on a positive displacement pump will be located where in a system. All right, so it's going to be flowing from the discharge side of a suction to the suction side of a pump. All right, it's not going to be from the suction side to the bilge. All right, it's relieving the pressure on the discharge side. And again, it's not going to be going from the suction side to the discharge side of the pump. It's going to be relieving pressure from only the discharge. All right. Here we have our 4 lobe pumps. This is actually a question from the Coast Guard. All right. So which one is having the correct flow with the correct direction of our lobes? All right. And the only one to that is B. If you look at our lobes, it's not going to have flow going through the middle. It's going to be just like a gear pump. All right. So question number 7. That's super weird. All right, there we go. Anybody else see that with the mouse? It's freaking out in the corner. All right. So on the pump shown, what is the part of letter B? All right, we're looking at it. So this is another Coast Guard question picture. All right, it's identifying what is on here. All right, you can see there's a lot more lines as well on a pump that I have taken away, all right, to only the parts that you guys have learned about. So looking at this, B is pointing on this line, and it's going to this internal part right here. That part is our impeller, all right? So this is a side view of our centrifugal pump, all right? Looking through, we can go into pump as well. We're looking at part A, all right? And that is showing the center of our impeller. So we're actually getting into a part of our impeller, but it's also pointing at the entirety of this area, all right? The only one that lines up with is our suction, our I, all right? Remember, we discharge at E. Anybody knows what D would be labeled? What is D?
That may be like packing material.
It may be pointing at the packing material.
Is it pointing at the drive shaft? Or the
It's
shaft?
Yeah, it's pretty much the shaft. I'm not going to hit you on the packing material since we didn't learn it. That's a 542 material. All right, when you dive into deep into pumps, there's a lot more more parts of a pumps, guys. All right, so these are your basics. So again, just what we did in class. All right, so it is your packing area, but it's pointing at the shaft. All right, for all intents and purposes. All right, and then what would C be?
Casing?
What would casing? Yep. All right. So that is our casing. So multiple choice here, a gear, lobe, and screw are all what type of pump, and that is a positive displacement. All right. Everything else answered here. We have centrifugal, kinetic, reciprocating. All right. What is kinetic and centrifugal? Are they what type?
Dynamic?
Yes, they're part of that entire category, right? Centrifugal is part of the kinetic category, right? And reciprocating is part of the positive displacement. But none of these pumps reciprocate, right? None of them utilize a piston type, right? All of them are a rotary type, right? Gear, lobe, and screw, all of them spin to create their positive displacement, all right? True or false, positive displacement pumps will send a fixed volume of fluid with each stroke or rotation of the pump. All right, that answer is true. Again, positive displacement does not care. All it cares about is sending out its next volume of fluid. That's all it does. All right. So let us begin today's lesson. Any questions on any of those quizzes? All right. So before we begin, all right, today we don't have 540 lab, because there is no in-person classes. I can't be there, and I'm not under any circumstance going to be sending you guys out to the ship to cause hazards or anything else like that. That just becomes a giant slipping hazard. So we are going to basically reconvene once we have, we go back to in-person classes. We'll find out later in this afternoon, I'm thinking, to whether we're going to be in person tomorrow. If we're in person, then we are going to be just going right back into it. All right. So if you have Tuesday lab and we get an email that says tomorrow we're going to have in-person classes, then tomorrow we're going to go back into lab classes. All right. If we get an email that says tomorrow's going to be remote learning only, then we don't have lab classes tomorrow. All right. So follow the guidelines of whatever is going to be sent out. Now, that being said, for everybody who is missing lab today and missing if you are going to miss lab tomorrow, all right, we are going to have to make up that time based on the fact that you guys need to have your lower engine room sheets done, and there is no time for us to just skip it into the next week. All right, so we're going to have to figure out times to meet and to get this basically into your heads. All right, so I'll be putting out something soon. I didn't expect crazy snowstorms like that this year. All right, so we'll just kind of continue on, look for emails. I will tell you guys during class, all right, once I've made a decision one way, shape, or form. All right, everybody else, you're going to just follow the schedule. And then next week, Monday classes, you guys aren't going to be doing lower engine room next Monday. You're going to be doing whatever the schedule is going to be telling you it's going to be done. All right? Make sense? All right.
Got it.
Keep in mind, our first test is still on the 10th, and we are going to have pretty much everything done either today or Wednesday, depending. Oh, and since we are online learning, I am going to be posting this to YouTube later today. So that way, if anybody's connection cuts out or anything like that. So we'll be back to doing that as well. All right. So let us begin. Everybody can see the PowerPoint? All right, good. Good, good, good. Let's change our pen color. Tired of red, go green. So before we absolutely begin, centrifugal pumps. All right, order of starting operation, start up. You're going to open all valves but your discharge. If your pump is primed, you're going to continue on to the next step of being primed. All right, so if you assume your pump is primed, and it is, you're going to open up all valves but your discharge. You are going to start your pump. All right, you're going to slowly open up the discharge valve. The tank is going to be filled. You are going to close the discharge valve. You're going to secure or turn off the pump, and then you're going to shut down. You're going to close all the other valves in the system. All right, that's a centrifugal pump startup. All right, if the system is not primed, you're going to open all valves in the system besides your discharge. You're going to open up your vent. Once you have flow coming out of your vent, you'll secure the vent. You will start the pump. You will then open your discharge valve slowly. The tank will fill. Once the tank is filled, you will close your discharge valve. You will shut down the pump, and then you're going to close all other valves in the lineup. All right. Now, with a positive displacement pump, a lot simpler. All valves need to be open, including the discharge. Start the pump. Once the tank is filled, you secure the pump, then you shut all valves in the system. All right. That's a quick reminder from what we did on last Wednesday. Steam reciprocating pumps. All right. Where do we have a steam reciprocating pump on our ship?
Is it pumping fuel oil?
Not pumping fuel oil. That's it is a positive displacement pump, but is a rotary pump.
Steam drum.
It's not in our steam drum. No, that's just going to basically be, it's actually the boiler doesn't have any pumps internal of it. All right, remember guys, I said this when we first introduced reciprocating pumps. All right, it's lower engine room. Where do we have a steam reciprocating pump? All right, this is going to be our import feed pump. All right. Now, this does not have the same level of flow as our regular feed pumps that we utilize. That is because when we're in port, we don't need to produce that much steam, right? Are we moving when we're hooked up, when we're on, we're at port?
Hopefully not.
Hopefully not. If we're moving, we're in a whole lot of trouble. So we don't need to be sending steam to our turbines, right? So this pump is still utilized. It still can create the high pressure needed. But since we only need to produce electricity and any sort of like domestic hot water and things like that, we just need to just get enough moving to keep the cycle going. All right, that's what this is about. All right, so when we would be in port, we would utilize our import steam drum, or import feed pump. Ugh. So we have our liquid end, we have our steam end. All right, so liquid end is our feed. All right, so our actual feed water. I'm going to switch over to purple so you guys can see it. All right, we have our suction and discharge. We have our exhaust on our steam end. Let me erase all ink on slides. And we have our supply. All right. So as we pumped there, watch our slide valve that we have right here. So right now we are feeding steam in. All right. The steam is being blocked from entering any direction. So it's going to flow here, but it can't access that side. It can't go into here. All right. So it has to flow into this portion. All right. Meanwhile, with this slide valve, every single part of the exhaust steam over here is going to flow outwards out of our exhaust. All right. So watch how that happens there. So as it slides across, we will have our pieces moving. All right. And it's either going to be opening one section or allowing the discharge to the other. All right. So that's how our steam reciprocating works. Now, we also use our main feed pumps. These work off a turbine. All right. So if you are in the lower engine room, all right, that is the shaft that goes out. All right. You have the stairs that are over here that are going down from upper engine room. All right. So this is going to be the starboard side. Correct. This is aft up here. This is forward. All right. We have our door over here that opens up from the outside. All right. We have both of our auxiliary condensers right here and here. They're in the air. Now, right here and right here, we have both of our main feed pumps. All right. Located right here is our import. FP for feed pumps. All right. And then over here, we have our 4 compressors for our shipboard refrigeration and HVAC. All right. So this is what we have. All right. So what we're talking about right now is our turbine feed pumps, our main feed pumps. Okay. So we have our exhaust. We have a drain down here for any moisture that may create. All right. We have our supply. Now we have a suction and we have 2 discharge lines that come out. All right. And then we have a recirculating line. Now, with our 2 discharge, we will get into this when we get into steam at the end of the year. We have our main and we have our auxiliary. All right, and that's our main feed and our auxiliary feed. They come out of the same line, but they have a major difference. One is regulated by a regulating valve, and one is not. All right, so our main is going to be with a regulating valve. Our auxiliary is going to be regulated via a hand valve. All right, so that's for emergencies, basically. All right, so if your regulating valve fails or it's not picking up what you need it to do fast enough, you can always open up your auxiliary feed. All right, so but don't worry about that as much. Just know right now that your discharge has a main and auxiliary line, and they basically do the exact same thing. All right, they feed the boiler with feed water. All right. Now, we have a pressure regulating valve that's going to be working off of lube oil. All right, this is our lubrication system. So we have our lube oil system. It sends out to different bearings that lubricate them. All right, and here's what it looks like in person that you can see. All right, we have our exhaust, we have our lube oil system, we have our recirc. Discharge is over on this side, and we have our suction and pressure regulating valve. All right. So you can actually see we have our 2 lines here. This is our pump side. All right. So we have both of our auxiliary and main lines that come directly out of our pump. All right. And then we have our recirculating line, which we will get into. We have our lube oil pump. And anything that says here, you can actually see it right there. It says OS trip. All right. Basically what that is stating right there is an overspeed trip. All right. So if this pump starts to overspeed, it starts to go and get faster and faster and faster, and it doesn't get to our rated speed that we want it to. All right. What it does is that if it gets too fast, it will trip it offline, which is basically the new word of the day for what we're doing here. Trip is going to be anything that's going to be an automation that cuts off either power or like anything that's going to be giving energy into a system. So this overspeed trip will shut off the supply of steam, so that way it doesn't continue to run and run and run and get higher and higher RPMs, and it will not break. All right, it'll give it time to slow down until it finally shuts down nice and gently. All right, so you can have many different types of trips. All right, this one is overspeed. All right, so if it goes above a certain RPM, it will trip it offline. All right, it will be basically, it will power cycle it off. All right, be like one of those things where your TV's being like really, really bad, and it's just glitching out, and you have all these different problems, and it's not even responding to a mouse, your remote or anything like that, and you just say screw it, and you rip the power cord out of the wall. All right, because it was not acting in the way that it should, and doing a hard reset like that will be better than just letting it exist at that level. All right, same thing if your computer is, frozen, blue screens, anything like that, you hit that reset button. All right, you're giving a trip to it. All right, you are turning off the power. All right, this one is for overspeed though. All right, so let's look at the lube oil. So it's a little bit of a system here, I will admit. All right, there's a couple of things going on here. We have our steam supply. We have a pressure regulating valve. All right, that is regulating the pressure going into the pump, into the turbine. All right, we have our overspeed trip right here. We have our lube oil return. That's going to return any of the lube oil going back into the lube oil sump. All right, the lube oil storage container for here. And we have our lube oil supply coming out of our lube oil pump. All right. So we have our feed water pump discharge pressure. So this is what's coming in. All right, this is our input right here. All right, so the pressure is going to be increasing because the feed water pressure coming out is going to be increasing. All right, so as it increases, it's going to push up on that baffle. It's going to overcome that spring force. And as it does, this pilot valve goes upwards and it blocks the lube oil supply pressure. You can see it's blocked right here, correct? So as that's happening, we can see that we have two ports that have opened up. All right. The operating piston drops below, decreasing the steam flow. So now this lube oil that's in this operating cylinder is going to flow outwards. And as it flows outwards, it fills up this area inside the pilot valve. It can't go anywhere else but down into a low pressure. All right, does everybody see that? So as our pressure of our pump has increased, just like a regulating valve, it's overcome this spring pressure right there. All right, it's pushed up on that baffle, and that baffle is connected to this pilot valve. Now, the lube oil in here is under pressure, and it comes flowing out. It fills this area. The only place it can go is down and out through the lube oil return back into the sump. All right, so since it's done that, the regulating valve will start to close a little bit. It will, as it closes, it's not going to allow as much steam through because this is our steam supply. All right, so that's how it's going to keep the pressure by measuring our feed pump discharge. All right, the discharge pressure that we care about is the fluid that we're pumping, right? Not the steam. And it will regulate the steam supply. Does that make sense? So we have now decreased the pressure. All right, so if we decrease the pressure of our pump, okay, look what happens. The spring overcomes the pressure of our pump. It pushes down on our pilot valve. And now look what's happened. It's blocked our lube oil return. All right, so now we have a lube oil supply coming in because it's coming from our lube oil pump. It comes in, fills this cavity. The only place it has to go is out and into our operating cylinder. And as it goes into the operating cylinder, it's going to push open our valve and it's going to allow more steam in. All right. A wider open valve will allow for more steam. All right, which will increase, in turn, increase our pump pressure. All right, does everybody see how they're correlating to each other as they're flowing? All right, and why knowing our regulating pressure is so important, our regulating valves. All right, for the most part, guys, it's going to be staying pretty normal. It's going to be regulating itself, but it's not going to have these giant dips and rises. All right, so with spring tension and pump pressure balanced, steam flow is pretty constant. The overspeed drip drops operating piston and shuts off steam flow. All right, so you could see how this bypasses this whole pilot valve system. All right, so if this overspeed trips, it will open up the valve and this will dump it all down into the lube oil return. No questions asked. All right. So that will shut this valve. That's how that lube oil trip is. It's very mechanical. All right. It would be like dumping open your bathtub's drain. All right. Nothing will be able to overcome that thing. All right. But there's one more portion that we even bring up is this reach rod. All right. So this is how we can have some manual input into here. So here we go. If our pressure of our pump increases, all right, we could see that it's going to push up against that spring. All right. But if we take this reach rod, let me erase all the ink on the side. If we take this reach rod, and if you notice, we're going into which direction? Are we righty-tighty or are we lefty-loosey there? Which way are we turning it? That's a valve handle stem right here. There's my valve handle stem. That's the hand wheel. If we're turning it which direction right now? We're turning it to the left or we're turning it to the right?
Right.
Well, the yellow arrow looks like it's turning to the right, but your arrow is turning to the left. I don't know.
So they're both turning the same direction. That I can assure you to. All right. It's just which way this looks. Is it going to be, is the valve handled that way? It's a weird image, guys. I will attest to that. All right. It really is. So we're going to say that this is turning left. All right. It takes a little bit to see it. But let's say that this stem is going up like this. All right. And it's going to the left. All right. So it's loosening. All right. So if we loosen this, what's happening to that spring?
It's expanding.
It's expanding. But what else is happening to it? if you push down on a spring, hell, even if you have a pen right in front of you, if you have a pen, and I grabbed the worst pen for this, jeez, and you have a spring in it, right, and you have it under pressure, right, and the more you push down on it, the more force is going to be applied to it, right? The tougher it is. And the harder it is to keep on pushing on it, correct? If you take out a spring and you try and squeeze it.
Yes.
So what happens if I go from squeezing it 50% to 25% less? So instead of squeezing it 50% all the way down, I'm squeezing it 25% down.
Would be less pressure, so you need less force to push it up.
Exactly. So by both relaxing the spring or creating less of a spring force, the pump discharge pressure set point will change, right? And will allow for a decrease in flow. Okay? So what's happening here is that if you have less pressure on that spring, it's easier for the pump pressure to overcome that spring force, right? If there's less force of the spring, which will make everything else here easier to accomplish. So as you loosen or relax this spring, you're going to change your set point of your feed pump. And as it does that, it'll allow it to flow out of here easier, and it will decrease the supply. And vice versa, if you change to make this tighten, all right, you turn it to the right and you tighten down on it and you go from 50% of your spring and you push down to 75% spring pressure, as I put my pen back together, what happens? What happens to the spring? What happens to the system?
It's going to be harder for the feed pump discharge pressure to overcome it.
Exactly. So if it's harder for it to overcome it, it needs more pressure to overcome it, right? So that means that it's going to increase the pressure of our lube oil and open up our supply. All right, so tightening down on the spring is going to open up our regulating pressure. All right, so that's how you can change the set point of how much pressure is coming out of not of our steam, but of our feed pump. Is anybody else as excited as I am about this? Because this stuff is pretty cool. When you see this thing working in real life, it is pretty awesome, guys.
It's riveting.
It is. You'll learn to love it. All right. So let's kind of continue on. All right. So this is what we can actually see. This is what is called a tracing. All right. This is a one-line tracing. And pretty much all it cares about is components. All right. If we look, we have like what looks like T's right here. All right. We could see it going this way on an elbow. They have different distances. I mean, to me, this looks like, I don't know, it could be like 6 inches. To you, it might be 2. Does the length of the piping matter here? Or the elbows, do they matter? Or the T's?
I don't think so. It's just a general idea. But I mean, like the ridges that show the pipe going over matter, I think.
Yes. So you're right. You're actually 100% right there. All right. So what's happening here? Let me get a better pen. Let's do red. All right. So what's happening here is important. All right. You can see there's little ridges that pop over. All right. That's kind of hard to see, so I'm going to draw it a little bit bigger. All right. So it's got a little bump like that, and then a line going over it. That means those two pipes don't connect. Okay. So where my little arrow is pointing to is this is just a bigger version of it. These two pieces of pipe do not connect each other. That's what that little bump means. All right. Now, the other thing is that the distance does not matter. All right. So on a real ship, the distance from this valve here to this valve here might be only 3 inches. This is not drawn to scale at all. They're never drawn to scale. It might be 24 feet. All right. The distance from here to here might be 30 inches, but it's the same distance as these 2 valves here. All right. It's all how the creator of whoever drew this decided to make it look pleasant, make it look nice, something easy to read. Okay. So the length of the lines do not matter. All right. So it's, like I said, it's component based. So we don't even care about if there's elbows. All right. So these 90-degree angles and these T's, in reality, this 90 may be 245s. All right. It may not even be 245s. It may be just a straight piece of pipe. All right. There might not even be a 90 between this valve right here and all the way to this valve over here. It may be a straight line. All right. But again, this is so that it fits on one sheet of paper. All right. So those 90s don't matter. And same thing here. That may be a T in real life, or what it may be is the line comes in here and the line comes in there. All right. And goes out that direction. All right. So you have to look at this component based. What it's showing is it's a flow diagram. All right, so we can see flow arrows. They're going to show the direction of where the fluid inside of the pipe can move. All right, the other thing that shows is all of the different types of pumps. So we have pumps here. All right, we have a relief valve because that's a positive displacement pump. We have different valves. Okay, so that's what's happening all here. All right. Does this make sense? So this is also, like I said, called a tracing. All right. Now, here is our manifolds. All right. This one is specific, a fuel oil transfer manifold. All right. So we have 3 solid pieces of metal. There's 2 sides to it like that. All right. And then we have a bottom piece. Now we have each one of these. All right. This can go to 1 tank. This can go to a 2 tank, 3, 4. So these horizontal pieces, how many ever spaces you have in between them, that's how many places this can go to. So this can go out to 4 separate different pipes, 4 separate different tanks. Okay. Now, each one of the sides, all right, since we still have that split down the middle right there, we have a fill and a suction. All right. Now, this is what's going on here. This goes to tank 1. This is tank 2. This is tank 3. And finally, we have tank 4. All right. Hell, this could be bilge manifolds. All right. And this can be bilge well 1, bilge well 2, bilge well 3, bilge well 4. Okay. But let's stay with tanks. Now, we have a suction and a fill. All right. Remember, we have this line that is going to be separating the 2 sides. All right. That piece of steel right here, going right down the middle. All right. So if we open the valve with the arrow, what tank are we going to be sucking from?
Tank 2.
Tank 2. All right. Does everybody see we going in, we're having, these are tank 1, these are tank 2, these are tank 3, and those are for tank 4. All right, so we're sucking from tank 2. All right, because it fills this whole entire lower cavity right here. All right, and the only place it can go is up in here, and it fills this entire area and gets drawn out through there. All right. I hope I can erase all of that. Yes. All right. So now, say it goes out to a pump. So this comes out, goes to a rotary pump, and it goes right back into the fill line like that. All right. Again, you're just basically pulling from one tank and you're going out into tank 4. And again, this fill is going to fill this entire side. But since tank 1's valve is shut, tank valve 2's is shut on the fill side. Tank 3, again, shut. 4 is the only one that's open. It goes down into 4, fills this lower cavity, and goes out to tank 4. All right, so that's how we can move fluid from one tank to another. And again, this doesn't take up that much room. All right, depending on how many valves in the system. And this can be like a 5x4 area. It's not that big. All right, which is great about this. All right, so does anybody want to go into not understand the fuel transfer manifold before we continue? Okay. So what's happening here is, all right, we're pulling. Let me get a different colored pen. I think actually I'm not going to do green because we're going to use that for filling. So we're pulling from this pump, this spot, this tank. All right, so we're sucking from there. So if we follow our line, we have a valve here we're going to have to open. It goes down, it jumps over that line, goes across here, goes up, and we have to open up this valve. All right, goes through strainer and into a pump. All right, why does it not go up here and go into those pumps as well?
The valve is closed.
Valve is closed. Correct. All right, goes up through those pumps, and now it's hit our positive displacement pump. All right, and we want to fill that tank there. So we're going to go from what? Tank 3 to 1, 2, 3, 4, 5. All right, we're going to fill tank 5. There's our pump. See, it crosses over and goes and flows outwards. All right, and again, this valve is closed, but it also has a check valve. All right, we could see it says swing check right there. All right, so even if that valve is open, it's not going to allow flow through there. All right, so if we're taking fuel in from the deck, all right, this is our fuel fill and discharge connection, port and starboard. All right, so we're taking fuel on. It goes and flows downwards through that valve right here that's on the deck, over and into our manifold. All right. We only want to fill those 3 tanks. All right. That's what the chief has ordered. That's what we're going to fill. All right. But if we want to fill something else, maybe. All right. Look at this. Why doing what we just did matters? What does that do for us? We went into the suction side, right? But it's still showing green like it's filling. So what did we do here?
Should you be making like a feedback loop with it or something?
Not doing a feedback loop. Follow the piping that we got, right? So it's coming in this way. Wow, that is a terrible color to go on top. Let me do that for you better. Do red. It's coming in this direction, right? And it splits off and goes that way. But it also is flowing straight up there. So why can we do that? Why would we want to?
Did we bypass it to fill it quicker?
Mm-hmm. All right, so we're just going to get double the amount of flow there. All right, speed is of the essence whenever you're shipping. Okay, if you are not moving, you're not making money. All right, and if it's something as silly as getting fuel, The company knows you have to do it, but God, they want you to do it faster than you should. All right. So you got to get her done. All right. So you open it up and you allow for a backflow, and then it's simple to just open up the other two valves in the system, and we can fill both port and starboard that easily. All right. So again, I'm not expecting you guys to know. I'm not going to test you on how do you fill both tanks simultaneously the fastest way possible and give you a blank sheet of paper. All right. But what you should be looking at here is the creativity of a shipboard engineer. All right. To do something faster. All right. We're still within the constraints of our piping. All right. So not every ship will allow you to do this. Some ships, you just got to be creative to what you're doing. All right. So here we have a bilge, ballast, and fire main. All right. We have a new word right here, which is sea chest. What are those? Who's heard of that before?
They store salt water to be used for the fire mains to extinguish fires.
All right. So this is our area, not just for fire mains, but it could be our saltwater system, our saltwater cooling system. All right. Or our ballast like we have here. So our sea chest, what they do is it's a spot on the deck, all right, in the hull. And most of them are internal of the ship. They look like this. So if you're walking around on the deck like this, all right, that's you. All right, you'll have a sea chest that looks like this. It's a box on the deck that pipes are coming out of. All right, there's the valves. And as you're walking around, this is where water can go into. All right, so salt water from the outside will be flowing into this sea chest. All right, it's just an area where you have sea strainers, you'll have the ability to collect all the salt water. They have bars underneath it to keep the bigger sharks and fish out of there and all that kind of stuff. All right, so that's a sea chest. All right. So here we have a bilge manifold. Now, these are quite different than a fuel manifold. All right, notice what happened right here. All right. So low pressure in the upper chamber is going to draw the bilge water up. So if we have a positive displacement pump that's going to be sucking from this direction, we're moving a volume, right? A volume of air out of here. It's going to create a low pressure area, and then it's going to pull any of the fluid that's out of the bilge into that area. All right. And it's not going to allow any sort of back pressure. All right. So if there's some flow from somewhere else by accident or a valve is opened, we're not going to flow in reverse. All right. Then we have ballast manifolds, and those are going to either be open or closed. All right. They're not going to act as a check valve. Notice their symbol difference. So this is our bilge, ballast, and fire main example that we have. All right, so we can go from bilges up forward. It can come down through our bilge pump and out to our oily waste collecting tank. All right, our oily water tank right there. All right, we're not going to be discharging this overboard, even though there is a line. That's really super illegal. All right. So this is our bilge and ballast pump. So if we want to go from, this could be our ballast system, anything like that. If we want to discharge that overboard, we want to deballast, that's what we would use this for. All right. Or if we want to take it from one ballast system and we want to pump it to another ballast tank, we could do that as well. And then this is our fire main system. So that is it on pump operation. Come on, why aren't you letting me grab you? There you are. All right. So we have 5 minutes in the rest of class. All right. That means there's going to be a quiz on Wednesday on pump operation. All right. So at this point, you guys have all of the information for test number 1. All right. The slides have been posted. They have been posted since last Wednesday. Someone in another class asked me if I could post the slides before class so that way they can use them when they're taking their notes. So I'm going to be starting to do that. All right. So you'll have the slides before we even begin the next section. All right. So that means test Wednesday. Test next Wednesday. We have a quiz this Wednesday. All right. On only pump operation. And we're going to go right into freshwater generation on Wednesday. All right. So next Monday, a week from today. All right. If there is any questions for the test Wednesday, I'm going to be giving you guys a little bit of the class if you have any questions you'd like to ask. If you don't have any, you don't come with questions, then I'm not going to just stand at the board and reteach anything. Okay. So if there's no questions, we're going to go right into the next subject again. And that's going to be freshwater generation part 2. All right. And a question is not, can you go over all the valves? Okay. So come with specific questions. Don't rely on other people to do it. All right. So that is a week from today. All right. And then same thing again, quiz Wednesday, test on the 10th. All right. Any other questions before I let you guys go?
Can you repeat what's going to happen with kids who miss the 540 lab this morning?
So yeah, 540 lab for today and or tomorrow, depending on what is decided by the college. Basically, that's going to have to be made up at some point because you guys need to have that lower engine room. All right. So there's a couple of different things that we can do. I'm going to figure it out. All right. I will let you guys know as far as makeups are going to be concerned. All right. You'll see an email probably within today or tomorrow. Okay. Depending on what happens. All right. It all depends on what happens for tomorrow's class is what I'm going to decide to do. Okay. And again, if we have remote learning tomorrow, that means there's no lab tomorrow. All right. But if the college says that we can attend classes, which looking at the storm outside, it doesn't look like we're going to have classes tomorrow. We're probably not going to have lab. Okay. So just keep an eye out for your email. And again, I'll let you guys know on what's going to happen for the kids that need to make it up. All right. Any other questions? All right. The only other thing I would give you as a piece of information is even if you're doing bad on the, if you're doing good on the quizzes, that just means I'm quizzing you on the stuff that you know. All right. Don't think that just because you have all 400s doesn't mean you're going to get 100 on the test. All right. It's going to give a lot more in-depth knowledge, and I'm probably not going to be taking any of the questions that I took from the quizzes. All right. So make sure you guys are going in depth of your knowledge of what's happening. All right. And if you're doing bad on the quizzes, study harder. All right. So any other questions? All right. You guys are all set. I will see you guys hopefully on Wednesday in person.
Adios.
Have a nice day.
Take care, Professor.
Thank you.
Have a good one, guys.